Statement of the Second Law of Thermodynamics. Welcome back to the channel. Today, we're exploring one of the cornerstones of physics and engineering, the Second Law of Thermodynamics. This law governs how energy behaves in the universe and explains why certain processes happen spontaneously while others don't. Unlike the first law, which focuses on the conservation of energy, energy can neither be created nor destroyed. The second law introduces a new idea: direction and spontaneity. It tells us not just that energy exists, but how it flows and transforms over time, and why some things happen naturally while others require effort. The second law of thermodynamics can be expressed in several equivalent ways. The two most common forms are the Kelvin-Planck statement and the Clausius statement. Kelvin-Planck statement: it is impossible for any device operating in a cycle to convert all the heat absorbed from a single thermal reservoir completely into work without producing any other effect. In simpler terms, this means no heat engine can be 100% efficient. Some of the heat energy will always be lost or wasted, usually as heat expelled to the surroundings. This sets a fundamental limit on engines, from car engines to power plants, explaining why they can never convert all heat into useful work. Clausius statement: heat cannot spontaneously flow from a colder body to a hotter body without external work being done on the system. This explains a very familiar observation. Heat naturally flows from hot objects to cold objects. For example, a hot cup of coffee cools down as heat flows to the cooler room air. But the reverse, heat flowing from cold to hot on its own, never happens naturally. To make that happen, like in a refrigerator, energy input is needed. Implications of the second law. The second law introduces several important concepts. 1. Irreversibility. Many natural processes can't be reversed without extra energy. For example, when you break an egg, you can't simply put it back together without effort. 2. No perpetual motion machines. It rules out the possibility of machines that run forever without energy input, particularly those that claim to produce work with no energy loss, known as perpetual motion machines of the second kind. 3. Direction of heat flow. It defines the natural flow of heat, always from hot to cold unless energy is added. 4. Entropy. The law lays the foundation for the concept of entropy, which measures the disorder or randomness in a system. Entropy tends to increase in isolated systems, reflecting the natural tendency toward disorder. Let's look at some everyday examples to better understand the second law. 1. Car engines. Your car's engine burns fuel and converts some of that heat energy into motion. However, not all the energy from fuel becomes movement. A lot escapes as waste heat through the exhaust and radiator. 2. Melting ice. When ice melts in a warm room, heat naturally flows from the warmer air into the cold ice, causing it to melt. But heat will not flow from the cold ice back to the warmer air spontaneously. 3. Refrigerators. A refrigerator moves heat from inside, cold, to outside, warm. This process requires electrical energy to run the compressor. Without this energy input, heat wouldn't flow against its natural direction, illustrating the Clausius statement. 4. Boiling water and cooling. When you boil water on a stove, heat flows from the burner, hot, into the water, cooler, causing it to boil and turn into steam. Once you turn off the stove, the hot steam cools down by transferring heat to the cooler surrounding air. Heat will never spontaneously flow back from the cooler air to the hotter steam. That would violate the second law. 5. Hot coffee cooling. Your freshly brewed coffee cools down as heat transfers from the hot liquid to the cooler room air. This process happens naturally and spontaneously. To warm the coffee back up, you have to add energy by reheating it, such as putting it in a microwave. 6. Human body and metabolism. The human body converts chemical energy from food into mechanical energy and heat. Not all the energy from food is converted into useful work. A large portion is lost as heat to maintain body temperature. This heat loss is a practical demonstration of energy inefficiency as predicted by the second law. All these examples reinforce that energy transformations and heat flows are not perfectly efficient or reversible. The second law of thermodynamics governs the direction and quality of these processes, reminding us that while energy is conserved, its usefulness declines as entropy increases. In summary, 1. The second law of thermodynamics tells us about the quality and direction of energy, not just its quantity. 2. It explains why energy transformations are never 100% efficient and why some processes are irreversible. 3. It describes the natural direction of heat flow, always from hot to cold unless energy is applied. 4. This law is essential for understanding engines, refrigerators, natural processes, and even the arrow of time in physics. The second law shapes everything from how our cars run to why we need refrigerators and even how the universe evolves. Understanding it helps us appreciate the invisible rules that govern energy and change. Equivalence of Kelvin-Planck and Clausius statements. We're going to explore one of the fundamental ideas in thermodynamics, the equivalence between the Kelvin-Planck and Clausius statements of the second law. Understanding this equivalence helps us grasp why perpetual motion machines of the second kind are impossible, and it's crucial for anyone studying energy systems, engines, or refrigeration. Let's dive right in. Imagine a heat engine working with only one heat source at a high temperature. Let's call it T1. Now, this engine magically converts all the heat it takes from this hot reservoir directly into useful work done, with no waste heat rejected anywhere else. This scenario breaks the Kelvin-Planck statement because it says a heat engine must reject some heat to a cooler reservoir to work. But here's where it gets interesting. What if we use the work produced by this perfect engine to run a heat pump? A heat pump is a device that moves heat from a cold reservoir, say at temperature T2, and dumps it back into the hot reservoir at T1. Since the engine produces all the work without heat rejection, the heat pump uses that work to transfer heat to fill, from cold to hot, without any extra input. That means heat is moving from a cold reservoir to a hot reservoir all by itself, without any external energy input. This directly violates the Clausius statement. This diagram sums it up. The heat engine breaks the Kelvin-Planck law by converting heat completely into work, and that work running the heat pump causes heat to flow backward, violating Clausius. Now, let's reverse the roles. Suppose a heat pump transfers heat from a cold reservoir at temperature T2 to a hot reservoir at temperature T1 without any work input. That is a direct violation of the Clausius statement because it means heat is moving from cold to hot spontaneously. Now imagine coupling this heat pump to a heat engine. The heat engine absorbs heat, Q1, from the hot reservoir, produces some work, W, and rejects heat, Q2, back to the cold reservoir. The key insight is, because the heat pump takes heat from the cold reservoir and pumps it back to the hot reservoir without work, the net effect is that the engine alone is absorbing heat, Q1, subtract, Q2, from the hot reservoir and converting all of it to work. This means the engine has become a perfect converter of heat to work with a single reservoir, violating Kelvin-Planck. Here, the heat pump breaks Clausius, and the engine breaks Kelvin-Planck. Together, they form a system that can perfectly convert heat into work, which physics tells us is impossible. So what have we learned? 1. The Kelvin-Planck and Clausius statements of the second law are equivalent. Violating one automatically means the other is violated too. 2. Both rules prevent impossible machines, like a heat engine with 100% efficiency or spontaneous heat flow from cold to hot without work. 3. This equivalence is fundamental for understanding real-world engines, refrigerators, and heat pumps, and why the second law governs all energy transformations. Remember, the second law isn't just a rule. It's the foundation that keeps energy flow realistic in our universe. If this video helps you understand thermodynamics better, please give it a thumbs up, share with your friends, and subscribe for more engineering insights. Have questions or want me to cover specific topics? Drop a comment below. Thanks for watching and see you in the next video.